Hello everyone. Today we're going to look at mole mass and number. You should have some paper or pencil, your calculator, and your handy dandy periodic table. So today we're going to just take a quick review at the meaning of mole and Avogadro's number and molar mass. And we're going to try and apply those concepts to actual calculations. Right? And you see our little strongman's back over here. So it is time to really pay attention. All right, so remember the mole was one of our 7 basic units of measurement. It is one of our key concepts. Be sure to review this. Remember, it just means a really big number of things. So number, that's just a how many. It's usually the result of counting. Okay? But we're going to be talking about very small things, number of atoms or number of molecules. So the connection between those two that we've talked about in class is Avogadro's number. It is now a defined value, and 1 mole of anything, whatever that blank should be, is exactly 6.02214076 times 10 to the 23, whatever that material is. That's a little excessive for us. We're just going to remember this number to 4 significant figures. So that'll have some factors, have some effect on our calculations. All right. That's not helpful, though, because we don't live in the world of counting little numbers, so we are back to our handy-dandy gram, another one of the 7 fundamental units of measurement. It's our unit of mass. So we need a way of connecting that, and our connection was molar mass, which we abbreviate MM. This is actually a measured value. It's the average molar mass of an element is that number right underneath the element symbol. And when we have a compound, the molar mass, we're going to add up the sum of all the atoms in the compound, all of their molar masses. All right, and this the most exciting part of all this is we can now connect our new things, the mole, to our old things, because the gram, remember, we've been working on this for a while, connects back to lots of other things, kilograms and pounds and milliliters if we know density. So we can just add our new pieces to the old, and we'll see how that works out. Okay, so here's again another way of looking at what we just saw. Our first 6 items on our chart are the 6 things we've worked with so far, right? And our new conversion factors, those new connections, Avogadro's number, the connection between moles and numbers of things, and molar mass, our connection between moles and mass of that material. So let's get to work. Remember, you can pause this video to work on some of the problems, and we'll walk through them ourselves. So make sure that you hit the pause button and give yourself a chance to practice these. Okay, first question. How many atoms of lithium are in 0.004400 moles of lithium? Well, I look at this problem, and I immediately see the question right at the beginning. How many atoms? That's what I'm trying to find. So that's going to be my finish point. Number of atoms of lithium. Okay? The word number of isn't in the problem, but it's kind of implied there by the how many atoms. How many? What number of them are there? Okay? And my starting point is what I've been presented with. 0.00400 moles of lithium. Now it's time to make a plan. Right? So I'll put my start at the beginning. Remember, MOL is our abbreviation for moles. And my number, the little hashtag symbol, number of atoms of lithium, is going to be my finish. It's at the end. I've got to find a way to connect them. So I ask myself, do I know how moles and number of things are connected? Well, the answer is yes, I do. It's connected with that wonderfully big number that we've had to memorize to 4 significant figures. 1 mole of lithium, 6.022 times 10 to the 23 atoms of lithium. That's our Avogadro's number. That's going to be our conversion factor. So let's set up the problem. We'll put our number of moles at the beginning. It's a 1-step problem. All right, now I've just got to arrange my conversion factor so that the units cancel. I've got moles of lithium, so I want that to cancel. I'll put it on the bottom. And my 6.022 times 10 to the 23 atoms on the top. Okay, now I'm ready to pick up my calculator. But before I do that, I'm going to think about significant figures. How many are in my first number, the number that I started with? And my conversion factor, remember, we have memorized Avogadro's number to 4 significant figures. It's an exact number, but we didn't use all those digits. So it's only got 4, so my answer should have 4 significant figures. My calculator gives me this answer, but I only need 4 significant figures. So this is a little tricky rounding. It's always troublesome with the 9 there. There's our results. All right, next problem. How many moles of scandium are in 49.6 grams of scandium? Remember, hit the pause button and try and work this out yourself first. All right, again with this one, the question's right at the beginning. How many moles? That's going to be my finishing point. Moles of scandium are in 49.6 grams of scandium. That's my starting point. That's what I've been presented with, grams of scandium. So again, I put my start at the beginning and my finish at the end, and I think, is there a way to connect these two? Well, I've got grams and moles. That was one of our new concepts, the molar mass. So I can do this in one step. But I need the molar mass of scandium. I need a periodic table. If you look right under the SC on the periodic table, it says 44.96. That means there's 44.96 grams of scandium for every mole of scandium. That's our molar mass. Sometimes it's written as grams per mole, but I like to write it as the so many grams equals 1 mole. Makes it look more like a conversion factor. Now we'll set up our problem again, a one-step problem just like the previous one, but our units are a little different, so we'll pay attention to those. We'll start with grams of scandium. My red conversion factor, I want to put the grams on the bottom so that that cancels out, and the moles on the top. Again, ready to pick up my calculator, but let me think about significant figures. Got 3 in my starting number, 4 in my molar mass. Remember, those are measured numbers. So my answer should have 3 significant figures. My calculator gives me this answer. I need to round it to 3 significant figures and include units in my answer. All right, ready to take it up a notch. This next problem's a little more challenging. Let's convert 4.03 times 10 to the 5 nanograms of potassium dichromate to moles. All right, so this problem's phrased a little bit differently. It doesn't have a question mark in it. It says convert this to that. Well, the this in this problem, the nanograms, is the starting point. And I'm going to convert it to, so my ending point is moles of potassium dichromate. Let's make a plan. Put my starting unit at the beginning, my finishing unit at the end. And I ask myself, can I make a connection between these? And the answer is, I feel like I should be able to, right? But I don't know how nanograms are connected to moles. I just know how grams are connected to moles. Right? But I know now, as soon as I hear it out loud, that grams also connects to nanograms. So I can put that unit right in the middle. And I'm going to have a 2-step problem. I can get from nanograms to grams because I know my prefixes. I remembered them from a long time ago. Right? 1 nanogram is 1 times 10 to the minus 9th grams. And now to get from grams to moles, I just need to know the molar mass of potassium dichromate. Well, how do I find that? I need the formula of potassium dichromate and the periodic table. So now we've got to remember how to name compounds. Here's where we're going to take a little pause. Make sure you pause the video and try to figure out the formula of potassium dichromate. It should take you less than 30 seconds. All right, there's the formula, K2Cr2O7. And to find the molar mass of this, I'd need to add up the mass of 2 potassiums, 2 chromiums, and 7 oxygens. When I do all that math, I get 1 mole of potassium dichromate equals 294.19 grams of potassium dichromate. Now I've got all my conversion factors either pulled out of my memory or calculated using the periodic table. So I'm ready to solve my problem. Put my starting material at the beginning, and it's 2 steps. So I have 2 spaces to fill in with my conversion factors. So I'll start with my red one, my prefix one, and I'll put the nanograms in the bottom to cancel my starting information, and the grams part of that conversion factor in the numerator in the top. And then I'll move to the second one, the molar mass, and put the grams in the bottom to cancel the grams in the top from the previous conversion, and the moles in the top. And again, I'm ready to pick up my calculator, but I'm going to check for significant figures so I know what to do at the end. I have 3 in my starting number, an infinite number. Remember, prefixes are exact numbers. They're from definitions, so an infinite number of significant figures, and 5 significant figures in my molar mass. So my answer should have 3. My calculator gives me this result. Now I need to round it to 3 significant figures. Again, there's a 9 there. That's going to, 9s are always trouble for us. So be careful in your rounding. 1.37 times 10 to the minus 6 moles of K2Cr2O7. All right, one more to go here. How many grams of iron are in 4.00 times 10 to the 25th atoms of iron? Again, pause the video so you can work it out yourself. And if you get stuck, turn me back on. All right. So again, question is, how many grams of iron? That's what I'm trying to find. Put that in my finishing spot. And I'm starting with the number of atoms, 4.00 times 10 to the 25th. Okay. So I'll put my start at the beginning, my finish at the end, and then I look and I realize I don't know how to get from numbers to grams directly. But I can do it because they're both related to the mole. So I'll put the mole in the middle, and then I will connect my beginning to the middle and my end to the middle. So between numbers and moles, that's Avogadro's number. We've memorized it to 4 significant figures. 1 mole, 6.022 times 10 to the 23 atoms. And to get from moles to grams, I need the molar mass of iron, and I'm going to find that on the periodic table right under the little Fe. 1 mole of Fe, 55.85 grams of Fe. So I've got, again, a 2-step problem. I put my starting amount in the starting position, and I'm going to let the units do all the work for me. I'm going to try and cancel out atoms, so I'm going to put that 6.022 times 10 to the 23 atoms of iron in the denominator, the bottom, and the mole part of my red conversion factor in the top. For my molar mass, I'm going to need the mole part in the bottom and the grams part in the top. Again, we'll check some significant figures before we pick up our calculator. There are 3 in the first starting value. Even though it's a number, let's be reasonable, we did not count there. So that is a number that is measured or estimated. 3 significant figures. Avogadro's number, we've memorized it to 4 significant figures. We didn't use the exact value. And our molar mass is also a measured number with 4 significant figures. Okay, so my answer should have 3 significant figures. My calculator gives me this result. It's a little bit of, again, a tricky rounding problem. But there we are, 3,710 grams of iron. All right, now what? Now what do we do with all this? We practice some more. Right? You've got tons of assigned problems in your homework, some additional worksheets. And it's okay to make mistakes. That's what helps us figure out where we need extra help. So make sure to talk to each other, visit my office hours, or make an appointment if those times don't work for you, and definitely visit the tutors in the Science Learning Center. They can be such a big help for you. All right, see you soon.